All right, we are recording.
We just got to
Sprints?
Yeah.
Okay.
Yeah, certainly feels like it.
You mean
Suicides.
blue line back to the
No,
goal line?
I consider that as a suicide. Like blue line back, red line back, blue line back, goal line, but we do mountains, so that's goal line back, goal line back. Through the middle. We do 4 of them. Well, we did 4 yesterday. And that was after we did like a full out, just sprinting cardio throughout just also of the hang skate.
Which this coach made us do suicides like after like an hour at one point because a kid threw a water bottle out the bus window.
Oh, yeah.
Like meat or whatever, and it shattered a car's windshield.
Ooh.
So we got to do an hour's worth of suicides because of that one kid doing that.
Oh, I feel really good on the ice today, though. It was not fun yesterday.
I know how it feels.
All right, so let's get started. What the hell's the matter with this monitor? Michael, you've been playing with this.
I haven't touched it. I play with your more expensive tool, the 3D printer.
Actually, last time I played with the 3D printer, so that broke it. I couldn't play with it anymore.
No, I wanted for a day.
Sucks, because I had some things I wanted to print. And that went by the wayside because I finally got pissed off and I just cut them on a wood. I know.
Oh, I see.
All right, folks. You two ready back there?
Yeah, sorry, you're just showing me what you're doing.
Tim, Laura, so we're still working on this design, and we got our page of gear, right? Decided it was 10 inches?
The 10-inch 100 tooth.
Okay.
Did we actually find one on what was it, Boston?
Boston Gear Catalog. I think that's where we got that
Boston
from.
Yeah.
Dynamics.
We got a, what?
Said I almost said Boston Dynamics.
Same place.
Actually, you probably, they may have gears.
I want to do a class like that.
All right.
That's not this
So we're good. We got our force. Let's go back to the picture here. So we're working on. Whoa, where'd you go? That was fun. So we can stop it.
Spreadsheet's doing something this day too.
We can chalk off that gear. We know what we're going to do with that now, right? Okay. We got to come up with a bearing. All right. Actually, we got to come up with 2 bearings. One here, one there. That also means we got ring grooves to worry about. The gear has a key and probably a set screw.
Actually, I don't think that particular gear did.
Didn't.
No.
Oh, that would suck. What else is missing here? And then we got the shaft design. And we're still at just kind of picking general sizes of things. Okay, we haven't gotten to calculations. I mean, we've been toying around a little bit with calculations, trying to figure out the pitch diameter and diametral pitch and number of teeth and all that sort of stuff, but nothing really towards the design itself. So the next piece would be, okay, who keeps pinging me?
No keyway, no set screw.
No keyway, no set screw. How do they plan on putting that bloody thing on there?
On the gear that we picked?
Yeah. Well, let's, we're gonna put a keyway in anyways, because that would just be horrible.
Is that something that is just machines the gear after the fact, and that be too difficult to do?
You do basically do what's a broaching process on the gear. It's cast iron, so broaching cast iron isn't really a fun thing. That would be a lot easier. Broaching usually, or cast iron is usually cast in, but let's assume it's steel and we'll cast it. Or not cast it, we'll broach it, slot it in. Or we'll worry about the manufacturer, we'll come up with one. How about that? Okay, so basic assumption on a gear. Somebody write this down. Better be me, because everybody on the other end can't see anything. So, where are we here? Basic assumption of gear. 10-inch pitch diameter, 100 teeth, and it is a steel, and we'll be nice, let's make it probably a waste of material, but let's make it 4140. Okay, and has a 1/4-inch keyway, and actually it's 1/4 by 1/4 when I say that. Okay, so we'll pick a key for that to go in the shaft because we're going to have something to hold it in place, and we'll make some other decisions along the way here, but so far good on that assumption for the gear. Okay. All right. So we are bearings. Oh, did we get it? We got a shaft diameter on that gear, didn't we?
Yeah, we did. Let's see. It was
1 inch, I thought, or 1.25 inches.
cup diameter. Did I hear that?
No, it'd have to be the shaft diameter itself. Maybe they don't give it.
Bore size 1.13 inches.
1.13 inch bore. You want me to bring it up?
So if you go back to that combination.
I mean, you can't reach the site.
Yeah, I think we're doing the YF 100 is what we chose. We're assuming it's made of steel instead of cast iron. So why would they use cast iron instead of steel on the gear this big? Because I noticed as the gears got bigger, they switched.
Cast iron has a really nice pourability compared to other materials. Not as nice as like bronze or something, but it the other steels, because they're a mixture of things, tend to have to be picked in a certain points to get it, where cast iron is a uniform homogeneous substance, so it flows nicely. That's the basics that I remember from that fun stuff, so I could be all washed up with that, but anyways, Tim, you following along on the Boston Gear catalog here?
Yes, sir.
Okay.
Yes, sir.
What else do we need on that? We probably could pick a pinion here, but I'm not really worried about designing that other piece. Okay? It's really just our task going to be looking at the shaft. So, all right, why'd they go out here?
What type of steel did we say we were going to make this?
4140. That'll give us the strength we need. All right. Anyways, back to here. So that's our bore diameter, which is from our fine friends at Boston Gear. So really got our first shaft diameter estimation. Okay. So you kind of see how this starts playing out. We keep going. All right. So we need to go find a bearing. Find bearings. Come on.
I'm guessing we could just assume pillar blocks since they're the easiest to use and most common.
Not in this particular case because we got to put this in a housing. So we're back to, and I actually took those little bearings away, but we're back to picking some of those sealed bearings. So let's go to e-catalog. And bearings.
That no signal gonna be on the level?
Where?
On the center of the. Give it a little tap, and it might go away. We can just ignore it. Work around it.
Join the Teams chat. That's what I did.
Join the what?
The Teams call.
Oh. Either way, that's just weird.
Yeah.
Okay, so pick a bearing, and what we're looking for is not in here. Flange mounts, pillow blocks.
We could go with oil impregnated, couldn't we?
Well, we could get away with a lot of choices.
That's probably more pricey.
Well, it depends on what it's doing. So I guess let's go have some fun here. So we may wind up back at a pillow block, but and then the other thing, the flange mounted would probably be working too if we just, depends on what the housing looks like. I mean, this was a piece of sheet metal over this thing. So with the pillow blocks, let's work our way through this one for a minute. Come on, open up. Give me a pillow block. View this item. Okay, so with this, as long as we can get the shaft in there and we could build something to hold this, we'd be fine. So we'd have to build a this scenario. Let me do a quick little snip here. Copy.
This project, don't forget, what is this gear system going to be used for in terms of loading?
We're just transmitting a 10 horsepower electric load from one place to another, reducing, we're not reducing, it's a 6-to-1 ratio.
Are
So
we assuming that there's not fluctuations in the...
Well, we got to make some of those choices too.
Okay.
Or did they put that in there that it was a steady load, I thought. But it's in the problem statement.
Just curious because of how strong you want the bearing to be.
Right. So if we do this bearing, So if we use this bearing right here, then we're going to need to design something underneath it that holds that up. And from that center point there to here has to be greater than 10.5 inches. No, 5.5 inches. Okay, so that we got room for the gear to work. Okay, so that's kind of that. Now you could build a housing that actually was something like this, where we had a bearing cup built into it. And let's do this kind of like that. Okay, where we put our bearing in here. That has got to be the shittiest drawing I've ever done. And our shaft's running out through there. So basically, we build that little end cap, basically, for the device. Okay? Make sense? So we got to make some choices. They didn't really specify any in their design. So a pillow block might work. Okay? That's one thing to keep in mind. Let's go do this, though. Let's go back to yeah, we'd have to bore it on the side, and the shaft sits in the end of it.
Yeah.
So that's doable too. So what makes these better or worse, I guess, is the $100 question, and could they be used? So these are bronze sensor bearings that have oil impregnated into them, so as they heat up, the oil film. And I still didn't look up that word for studying of oil and how it behaves. So it'll come back to me. Well, it just did come back to me, but it'll come back to me after the class is done. I won't need it. So as long as the inside diameter is right and we have the clearance we need, as it heats up, the oil will separate out and become the film that needs to keep the shaft lubricated and keep it floating in the center of the bearing. And then the other part about the bronze bearings is that they wear fairly well. Unlike steel, they're meant to actually be worn away. Not worn away, I mean, you don't want them worn away in 5 minutes, but they'll last a long time, but they're meant to be consumed down the road and got rid of. So they are doable. The nice thing about these is they save a lot of space. Because they're thin.
It's just a piece of metal.
Yeah, it's not a whole assembly of things. Now the other thing is these don't usually operate on high-speed stuff. Okay, so 10 horsepower, and we decided it was what, 300 RPMs?
I think we changed the horsepower down to 3 horsepower.
Okay, so 3 horsepower. What was our RPM?
500 is what I have.
500. Okay, so 500 revolutions per minute. On a 10-inch gear, let's figure out what the velocity is. So the fun things you do in dynamics. Come on.
Well, we're 500 down.
I want to know what the velocity is of this gear rotating around 10 inches at 500 RPM.
Dynamics of other days, a lot of times.
Well, so think about it. What is it I want to do? Pigeons in the background here.
My brain's churning.
Yeah.
Cool. You can Google it too. I don't have a heartache with that.
No, that's right. I actually agree on that.
If you remembered everything, I'd be really impressed.
Yeah.
I'm usually
That's
pretty
definitely
good.
not bad.
I vaguely right now have a solution in my head, but I don't have it, so don't look at me. Tim, do you know how to calculate velocity out of RPMs in diameter?
Not off the top of my head. Not off the top of my head.
Say that again.
Not off the top of my head. Not off the
Okay.
top of my head.
I got equations.
What do you got?
I got 2 pi times d over 2 times your RPMs over 60.
2 pi d over 2
times RPMs over 60.
Okay. So what is 2 pi d over 2? Or pi d, basically. So circumference is equal to 2 pi r. 2 pi d over 2 is pi d, which is still the circumference. And I take the circumference and I multiply it times the RPMs, n, and I get inches per minute. Does that sound like a velocity to you? Sure does.
I'll divide by 60 and convert to seconds, just per second.
Right. So we want to get it in miles per hour, so you have some perspective of this. Do it. Let's calculate it. Give me a number. That is annoying.
$262.
262.
Yeah, that's what I got.
What do you got?
262, and that's inches per second.
Oh.
Okay, so inches per second to feet.
Let's see.
I mean, I wanted something that you're familiar with.
21.2
21.82 miles per hour.
feet per second.
Feet per second.
It's a lot.
It is. What's in miles per hour?
Oh god.
Do you know what feet per second looks like?
I mean, I can picture a foot, like, getting
22 feet.
22 feet
In 1
a
second.
is a
Okay,
lot.
that's fair. So that's all I'm looking for here, is if you get some perspective of it.
Yeah.
But most people can put things in perspective of miles per hour because you all sit behind the wheel and put FaceTime on the windshield, right?
How fast is it? 22.8 feet per second?
21.8 feet per second. Slow down.
That's 14.
I mean, I'm
15
checking that.
miles an hour.
Yeah.
This originally is inches per second, right? Or inches per minute.
Well, it's going to calculate inches per second because we're taking the minute RPMs down. And really, you do want inches per second because that's the way we calculate it to figure out all the mechanical stuff.
Right.
But you need some perspective of that. Until you get to the point you know what an inch per second is, you know,
But in terms of.
put it in terms of something you know, right? So 15 miles per hour. Is that fast?
I mean, for
For a
something
bike.
For that little gear? Yeah. Okay. For the car? No. No. I'm sure Tyler can actually run faster than that. All right. So, anyways, so what it comes down to with the gear or the bearing for the shaft is we're interested in whether or not we need to go to a ball bearing because of the velocity? Or can we get away with censored oil impregnated?
Probably not, because it's just such a high velocity. Probably not.
Probably, but I'm not going probably. We're at the point where we're shopping from the manufacturer. So let's just see what the manufacturer's got to say for its RPM. And I watched it, James. Michael's getting his marshmallow shooter ready to go.
Oh boy.
We got the other part in there, so
Take cover.
take cover. Yeah.
If you can hit the no signal sign, I'll personally vouch for you. All right, so we got to go back to Boston Gear and actually look up some specs here on the.
Most of the ones I'm looking at, I haven't put in sizing yet. I'm just looking at the bearings in general. A lot of them seem to be able to take 1,200 feet per minute.
Okay, so you had 22 feet per second.
Per second. So what's that per minute? 13, 20 feet per minute. So it's about 100 too much
Yeah. So for the bronze.
for most of the bronze. I haven't
Okay.
put in sizing.
So no, that's fine. But that's kind of what we're using to make some choices here. See what I'm saying?
Yeah.
Tim, you see what I'm saying? So we're about 100, you said?
Yeah, we're at 13, I think I had 1320, and the max velocity is 1200.
Okay. So 1200 is the max 1200 feet per minute is the max velocity for oil sensor. Let's go back and take a look at our other friends here on the pillow blocks. I'll just pick one.
Not seeing any max velocities in this.
I don't even see any details.
It's just supposed to be it will take everything apparently.
Well, that's not always right either. But we are, so you're kind of looking for those things that can actually handle this stuff.
Mm-hmm.
So let's assume that a pillow block actually works. So we need a pillow block that's 1.13 inches bore diameter.
Remind me what a pillow block is?
This thing.
Oh, okay.
It's called a pillow block because it's this cast iron piece of metal around it.
Right.
And the bearing is pressed in the center. So
Oh,
it's supposed to give it a smooth, pillow-like rotation.
makes sense.
That's how it got its name. I have no truth really other than
Makes enough sense.
somebody thought of it in the 1900s in the 30s.
So
The cool thing about these folks are the grease skirts on, they can be lubricated. Okay? Where the oil impregnated, once they're in, they're in. Okay? The other thing is if you're looking at something that was going to be encased in a housing, you want that oil to splash over everything.
Right.
Okay? Which is why I'm not so sure on car engines anymore because they got the oil pumps, but on lawnmower engines, at the bottom of the crankshaft, when it goes down to the piston's bottom dead center, there's a little piece of metal attached to the bottom of the connecting rod, and it basically splashes oil. And it dips. It's called an oil dipper. And it goes down and dips the oil out of it and splashes it up on the cylinder wall. So that's how it lubricates itself.
Right.
Okay? With oil pumps, we've gotten away from that because we take the pump and run it through a filter, suck it up into the pump, push it up into the block, and squirt it out where we want.
Right.
And that's how that works.
It's really crazy to me just how simple some stuff is for them.
Oh, they're really simple. Problem is, they're just not as efficient as we'd really like them to be.
Yeah.
Okay, so we need a pillow block here that's actually going to be our right size.
So with the pillow blocks, I was looking at the sizing for the bore diameter, and it seems like the closest one to what we want would be 1.125. Would that make sense if our
Yes, if the shaft is 1.13.
here is 1.13? Okay.
Yep. Which could be really fun. So 1.125 is an inch and an eighth. 1.13 is the inch and an eighth also. And it's just the 5 rounded up to the 2 to make it a 3.
That's it.
The basic size is there. Now we need to worry about our specific size when we get down further. Okay? Okay, so we have, what model number, which was the model, first this, model number for the bearing is?
Cast iron bearing here for a pillow block, but 6H1 1/8.
6H 1 and 1/8.
Yeah. With a dash between the 1 and 1/8. Yeah.
Like that?
I'm not describing it wrong.
Oh, yeah, okay. So it is what I thought it was.
Yeah.
But they just put the dash in between the 1 and the
I
1/8.
don't know if it's important for looking it up in the catalog later.
It may be. Okay, so there's our bearing. Its bore is 1.125. Cool. Now, the only thing is it's going to be hard to modify the bearing internal bore.
Right.
So down the road, we're not going to be able to adjust that.
It's not like you can put a drill in it.
Yeah, because it would just spin. Okay. Sure, somebody's tried to figure out how to ream that out, but you'd have to hold it in 2 places and go buy something else if you got to go to that kind of effort. Unless it's a do-it-yourself project and it's the only thing you got handy at the time. Yes,
Try and punch your way through it, like, kind of like a ream.
but I wouldn't go out of my way to tamper with this if I had an entire resource at my disposal. Go make your shaft something else.
Get a
Okay.
little bit of sandpaper, 10 hours.
Yeah. Dremel.
That might do it.
Yeah. Okay, so we got our bore, or we got our bearing, we got our gear. What was the model number on the gear? Do you remember?
The gear was the YF100.
YF100 is our gear. Cool. All right, so we're back to, hey, we might be able to rep. Stop doing that. Okay, so we got our bearing. Yes, we got our gear, we got our other bearing, and we got initial start stuff for our shaft, right? Okay. Cool. A nice thing too about a pillow block is we don't have to put a ring groove in to hold the bearing in place, and we probably do not have to worry about what am I thinking here? Thrust bearings. We don't have a need for a thrust bearing. Okay.
You probably want to do a shoulder still, right? And not do a ring groove, or...
Well, we gotta think about some of that. Yes. So, we good so far here?
What did you say?
The fillet.
Yeah.
Essentially, create a good shoulder on
All right. So,
the bearings on the inside.
I think personally we got all the general details of what we need. Okay. We don't really know what this outer housing looks like other than they specified it was a piece of sheet metal. But what I'm really interested in is we can design the shaft, select the bearings, put the gears in, and all that sort of stuff. So
You wanted us before to also find the small gear, right? The pinion?
yeah, we could come back and work on this one if we got time. Let's get this one done. Okay, so if we can design one shaft, one gear, and the bearings, we've accomplished this semester's goals. Okay. All right, so let's do this. Let's set this up. We have a pillow block. And as long as I'm having fun here, let me teach you some basic sketching stuff. Alright, so when I draw a gear, it looks just like this, except what I do is I come up here and I go that, and that represents schematically a gear because that is the pitch diameter circle. Okay?
Because I noticed that a lot of drawings do like 2 X's.
Yeah.
Is that standard? Or?
So they can do that. Yep. Okay. In this particular case, I'm going to specify we got a pillow block. So, and we'd want to do part 1, part 2, part 3, and we'd want to start over here, part number, description, and then we do quantity and whatever else we need. But right now we're just going to do part 1, description, pillow block. It was what number?
For the
pillow block?
Yeah.
It was
6H.
6H1-20.
Okay. And then we need 2 of those. Okay. And then 2 was the gear. Actually, spur gear to be appropriate name. And its nomenclature was a YF100. And we need 1 of those. Okay. So as I keep going down this, we're going to keep adding to this. And then we got a shaft, which we're going to develop here. We need 1 of those. Okay. Okay, so the shaft is something that's going to rotate, okay? And we are driving that off a pinion. Going to rotate this thing, and we want to know how we're going to hold it in place. Okay, so we know we got a key. All right, so now we're going to put number 4 is our key. Okay. There is nothing to keep this from sliding left or right on here once it's there. So we can use a couple things. We can, if it's low enough torque, I could use the set screw on the key and the set screw on the shaft. So 2 set screws on the gear.
Right.
Make sense? Or I could put a lock ring so that it stays where it's supposed to go. Doesn't slide left or right.
The lock ring is like 3/4-ish circle or something.
Yeah,
Point.
they have this kind of shape to it.
Alright, cool.
And you're talking for the gear for that? Or for the gear and the bearings?
Well, the bearings are going to stay pretty much where they are, but the shaft, we have nothing to keep it from going left or right at any given time. So if something's misaligned, it's going to slide. It's kind of cool. I actually watched discussion on the Millennium Bridge in England the other day, and it was as people walked, and it wasn't more about systems lining themselves up. So have you ever seen metronomes on a wooden table? They will all start out of sync. By the time they're done, they're all in sync. And it's because there is a natural harmonic that goes with things. And if you set things so they float and they can move, set 2 metronomes going in time, set one out of time, and these 2 are always doing this. One rolls to the right and rolls to the left, and rolls to the right and rolls to the left. Well, the other one's rolling left and rolling right, and this is rolling right and rolling left. So it's opposite. But what will happen is they'll become a half sync out, and this one will actually start to change its frequency to match the rest of the table. So they all change. Same thing happens on the Millennium Bridge, which really was, I thought it was just the wind that was doing it, or just the up and down motion. It wasn't. What was causing people sickness is every time you walk, people became in step out of natural rhythm, but not because they were trying to be in step. So, and what it also does is this: as you step with your left foot, there's a little bit of push of your body to the left to transition to the right foot. Just like skating, which is, I was thinking about this earlier. It is that motion that people walk. All right. And what happened was enough people were causing the bridge to go one way, and eventually the bridge starts to compensate, and everybody starts swaying with the bridge.
Oh.
And they became all in sync. Well, as they did that, they kept shoving to the right, shoving to the left, shoving to the right. They actually figured out it was 63 people could do this. And they just started out with a bunch of architects and engineers sitting there going, okay, somebody walked across the bridge. It didn't sway. And they had frequency meters on it, so they were really measuring this thing. They got to 100 and they didn't do it. Or not, let's see, must have been 600. But as they kept creeping up on the numbers, they finally got to a point where it just started swaying. So literally, you can walk the bridge safely as long as X number of people stay below that point.
I'm looking at the Wikipedia right now. They need to close it for 2 years after they open it.
Yeah. People wouldn't walk on it.
Yeah, they said at the first day people were.
So
It sounds like galloping gradient a little bit too.
it is. Well, it's all similar to that.
Yeah.
So anyways, with this shaft in this conundrum of parts and pieces we got here, something shouldn't move. Okay? We want the shaft to rotate on these things, but we wouldn't want it to be misaligned and go left, for instance. Okay? Which is why when I go back, the pillow blocks are a nice idea, but the gear or the housing that the bearings put in it puts a piece of metal at the end of the shaft so it can't go anywhere.
Right.
So it kind of locks it in.
That's kind of why I wasn't sure if we wanted to try and do shoulders at the pillow block or not, because, well, I think the gear has a larger diameter to start with by, you know, what is it, 5 hundredths of inch
Sure.
or something like that.
That's not a lot of strength when you had to fill it in there.
Yeah.
But we could find something with a little larger hub,
On the inside.
or we could take the gear and bore it out. Right? So you buy stock parts, and sometimes you do modify.
Okay.
Okay? So, is what you're suggesting this?
And that's the shaft?
Yep.
Yeah, that's pretty much what I was thinking we could possibly do, because then it can't really, I mean, it would have a little bit of wiggle, but it wouldn't be anything drastic.
Right. So, and then we got a keyway right here. All right. So, the interesting thing with that is we can keep the shaft basic size and step the bearing ends down and find a different bearing. Right? So the chances are we could find a 3/4 inch bearing. Yeah. Okay. Now what? What's the next thing we got to worry about? So I got a key that'll keep the gear rotating with the shaft. How do I keep the gear in its rightful home?
And that's what I was thinking. We need those lockers.
The lock rings.
Yeah.
So we need some ring grooves around that position.
Right.
Okay. Now let me ask you another. Okay, so next edition here. So we're going to put ring grooves in to hold our shaft in there. Okay, so what if what if we did a step shoulder there?
Save you from having to buy the locker.
Right. And the other thing, if I take a look at the gear hub, so let me really practice my, you guys missed it. Was it last year? Or was it in Strength and Materials last spring? I can't remember. But I started laughing because someone was always asking the question about, why do you do all that sketching? It's because it's engineering artwork. So I got the point. I was just going, hey, I'm going to do some engineering artwork. So we got a hub like so. Going up, and whoops, we got to have a keyway in there. So out here someplace is the rest of the gear, but there's the hub. So we could put a, yeah, let's do this in something blue. If we wanted to lock this in, we could put a set screw in here. That pushes down on the key. Okay, and that would keep us locked against the shoulder. So let me ask this question, and this is where the fun comes in choosing what you design. So if I can guarantee that that set screw is going to hold that onto the key and push it towards the shoulder, do I need the ring gear or the ring groove? Probably not. Okay. Is it going to be stronger with the ring groove or with the set screw? So we've got to do some calculations at this point.
Yeah.
Okay. Now, here's the thing that I'm doing to you, without you even realizing it. I think I missed an O in there. I did, didn't I? Philosophy. So, create 3 designs. And then check them all. But maybe out of those 3, you'll find a 4th one that pops out and says, oh, I never thought about that one.
Right.
And then, guarantee you'll always wind up with a better product. Okay? It's the bad designer that actually just takes the first one and runs with it. Because, yeah, did you look at any other potential problems? No. Well, there's probably are some that you need to look at, okay? Okay, so, we are getting really close here. All right, so we know we got, well, so literally, design 1, design 2, design 3. Okay? Is there any of those that really strikes you better or worse? And then you've probably all suffered a little bit with Dr. Craig in decision matrices. Also quality. No?
And
I don't know.
no.
He's always, not that he's wrong. It is the way to go, but he tends to put that on everybody for projects.
No.
We haven't done any
Yeah. Honestly, this year.
Okay. So usually what you try to do is you weigh these against something that's customer specified.
Right.
Okay. So for instance, Tim, let's say you were the customer and you decided that we needed a shaft that was, 1 1/8 inch. Have we met that? Yes. So we go over and we put a 9 in that box. Okay, and I use a little weird system. I use 1, 3s, and 9s because they're an exponential growth. And to me, it makes things that are really important way out faster, and those things that aren't so bad just drop away. Some people use 1 through 5, and try to rank them that way. Depends on where you learned it from. The guy I learned it from was exponential. Mike, just do it. It's like, oh yeah, okay. I can do it. So, Tim, give me another specification that you might want it to do.
Longevity.
Longevity?
weight, maybe?
Okay, we got weight to deal with.
Maybe it starts and stops a lot, so that the 3rd design would be bad. It's harder to start.
Shaft would be 1.125 inches. Weight?
Was that size, then design 3 wouldn't work just because the gear's bore is already at that size.
Yeah, but let's just assume right now. Give me some other parameters here
Okay.
from the project spec or things that does it need to be self-lubricating?
Use and maintenance.
Service hours, how much it's going to actually run for.
That's your longevity, but I like service hours. Okay, what else? Actually, I'm just going to do lubrication, and we'll.
Specify.
Yeah, and we'll specify by self-lubricating. If it has a high importance, we'll give it a 9. If it's not auto-lubricating, if it's something we can grease, that would be the 9. So we'll make a decision there in a bit. Okay. Longevity, lubrication, weight. Stock parts. Okay, because if I can do stock parts and I don't have to make a bunch of stuff, it's cheaper for the customer. So then we get down to final cost too, which would be one. Not usually the one that in an engineering scheme I'm worried about, but it's something to do with that. Okay. Okay, let's just play with those for a bit. Okay, so we've already decided that a pillow block would work, but we did look at bronze oil impregnated bearings, right? So those are kind of self-lubricating. So we already know that If it's self-lubricating, that's a 1. And if it's manual, that would be a 9. Okay? So that kind of gives the customer's perspective on that. Weight. High or low on the weight? Which one's going to be the better one?
It depends on use case. Like, does it matter? Because
I'd say
if it's going to be running all the time, it shouldn't matter.
So let's go back to
Well, are we talking about weight of the whole system or the load on the system?
well, all of that.
Because if it's just, if we're talking about like the weight of the system, you know, the gears and the shocks, that's not that hard to account for.
Right.
But if we're talking about the load, then that's a pretty big deal.
So we got bearings that need to support 50 pounds eccentric loading. Okay. So that's something they gave us. That's a criteria we got to meet. Okay. We got our hours, 25,000 hours. Okay. And what else? It's a prototype, so we're not hung up on, we're going to mass produce these things, right?
Right.
I think that's about it. Yeah.
You show you show the orientation of everything with all your micro so far.
Right.
Yep. Okay, so so maybe the weight actually applies to not the weight of the shaft, but it's the 50-pound force eccentric loading. Okay. All right, so what I do across this is I go design 1, design 2, design 3. Okay. And let's blow out here so we can actually see everything. So if we take a look at this, design 1, shaft, we're good, right? Oh, 9 would be good. Service hours, we're looking at, well, we could do 25,000 would be the target. Let's call that a 3. And if it's more than 25, let's do this. More or equal to, that becomes a 9. No, more, that's less than equal to. Jeez. If it's less than 25, okay, that becomes a 3. And if we have some stupid number out here like 1,000, that's a 1. Okay? And you assign those numbers to it. You got to give them some sort of parameter so you know what you're evaluating against. Okay? So design 1, shaft, everybody gets a 9, right?
Well, 3 would be less because.
Okay. So 3 is going to be a 3.
Sure, yeah.
Okay. Longevity, we're going to assume that they're all 9s. We'd have to actually do some numbers here, but we also know longevity could also go for just the bearings too.
Is this a rating for how well, in terms of that category, they're going to perform, or how important?
Well, they think they're going to perform to meet the customer's demand. Okay. And literally, it's along the way we kind of hopefully take the parts that we're going to do this. But in order to evaluate which design I'm going to go with, I use decision makers to do it. Okay. And believe it or not, Corning Glass has a really interesting one they use, and their chief engineer showed it to me one day, and it's cool. Okay. Weight, did they all handle 50 pounds? Okay. Lubrication, we chose bearings that were going to be manually lubricated, right?
Yeah.
Stock part,
All night. This is all stock, right?
yep. Okay, so now I'm stuck between design 1 and design 2. And truthfully, there's got to be some more categories in here, but I'm missing them. I would add another category for ease of manufacturability.
Right.
Okay? Shaft 1 is really easy to machine.
Just a straight shaft.
Stick a piece of rod in it and call it done. Okay? Maybe cut a keyway in it. Okay? 2, we got to machine both ends. Okay? And then 3, well, we got more machining, but we get a much more rigid support for the gear.
So that might be another category that we would add.
Well,
Or I guess that would be under longevity to some extent.
With 2, you'd have to machine the regulars too, right?
Oh yeah,
So I think the design 3 would be easier to machine than design 2. So you only have to do the one rigger.
well, all right, so let's talk a little bit about process of machining here. And don't let me go over time today because I got to go up to the president's office at 3.
You got 3 minutes. Well, yeah, you got
Yeah.
15 if you want to go to 2.
No, I got to walk all the way across, plus I got to go to the office. pick
Give
up all
yourself
my
an
stuff.
extra 10 minutes.
So on 1, I don't do anything other than make sure it's the right diameter.
Right.
Okay? And maybe put the groove in for the key. Okay, so the keyway gets put in. Cool. All right, that's really cut it off, face the ends off so I got a nice end, put a bevel on it on each end so they're not sharp, and then take it to the machine, a milling machine, and cut the groove for the keyway. Okay, cool. So literally 3 processes: cut, face, bevel, slot. Throw it away. I'll throw in the bin for the next. Okay.
Right.
2 requires me to take cut, face, because we always face both ends off on a piece of metal, and then I'm going to step down one end, and then I'm going to step over and I'm going to do the ring groove, I'm going to do the other ring groove, and then I got to turn the part around and put it in another machine, or turn around the same machine and face the other end off, okay, which is perfectly fine.
Right.
Or it could be this. I cut this end off, I got a long rod sticking out of the machine. I face this, I cut the groove, I cut the ring, but each time I cut that, the machine advances the part further up. And there is a part rest out here someplace in the process that holds up the end of the shaft.
Right.
Okay? And then it advances far enough, I go over, I do my facing, I do my trim for the shoulder, and get down to the right diameter for the bearing, and I part it. Part drops off, part goes over to the milling machine, puts the slot. Okay? So there's 2 different ways to manufacture that part. Okay? The third one, I got to feed the part out, face it, shoulder, put the right diameter, put the right fillets in, all that sort of stuff, put the little bevel on the top here. Every time I make a sharp cut, by the way, I'm putting a bevel in, so there's a step in the process.
Right.
Then I'm going down, I'm going to do another step, and I'm going to machine this down the diameter. Then I got to feed it out, machine this down the diameter, and part it, and send it over to the milling machine for key. No matter how I do this, I still got key slots to put in another machine altogether. So,
Design 3 might come up with more weights.
yes, design 3 will come up with more ways, because I'm going to have to start with the larger. So if it's 1 1/8, I probably want to go 1 3/8. I've got like a 1/4 inch stock on there for the shoulder.
Right.
Okay? It wouldn't do much to have more stock than what the bearing actually going to bear against. So there's that bit to play in there. But this is one of these things where, so you're the designer. There are a whole group of manufacturing engineers out there that will tell you how to make the thing.
Right.
So you're trying to make it manufacturable for them, and this is a point in the project where you go, hey, come on with me, James, we can go talk, and you're on my team now. Okay? and we get you to look at it and go, okay, I'll do this and this and this and make it. Okay? Whereas if I'm just dreaming it up, I don't give a damn. Somebody will make it. That's not the way it works. Okay? So we always want to make things that are manufacturable, so it doesn't take forever.
So come up with your best design of this process, and then maybe get the manufacturer engineers or whoever's on the floor, or would you bring them maybe two of your options, your best two, and say which one would be easier?
Well, I hope your chief engineer will actually be putting a team of people together
Yeah.
so that they know we're going to make this and we got to get it up to be made eventually.
Yeah.
And you're not just doing it in your own little spectrum.
Yeah.
Never works that way. Okay, so here's what I want you to do for Thursday. Tim, Laura, you listening okay? I would like you to take the shaft, come up with a decision matrix that you like, and you can put as many parameters you want in there, okay? The more the better, so you can come up with a good judge of which one's the best of these three, okay? Then I want you to take the one you design, figure out the forces on it, and start doing the math that goes with the beam design, or the shaft design, okay? And you each can choose your own different design. And then Thursday, I'll take a look at it, and we'll try to get it towards final completion, okay? And then make some good sketches along the way, and next week I'll have you hand it in. Fair enough? Okay. All right, folks. Y'all have a good day. I'm going to go have some fun with the president.